Hello everyone and welcome to our webinar on geographic optimization with Bayesian networks and BayesiaLab. Thank you for joining us today. Let me start off by sharing with you today's program overview. Momentarily, I will introduce our webinar team. Then I'll do a quick introductory demo of BayesiaLab's mapping capabilities. After that, we'll get into the into the really interesting part and show you how to use Bayesian networks in perhaps unexpected ways. In particular, example 1 will be about computing drive time bands, and then example 2 will be about hub location optimization. But let me start by introducing today's webinar team. On the line with me today are Stacy Blodgett in the middle, who's our customer relations manager. And then the picture on the right shows Claire Gora, who is our director of sales. And she is joining us from Toronto today. Finally, my name is Stefan Conradi, and I'm the managing partner of Bayesian USA, and I'll be hosting this presentation today. Now, I think there are once again quite a few people who are joining us for the first time, and therefore I think I should clarify some terminology, as pretty much every other word I will be using today relates to Bayes. So we have Bayesian, that's our company, that's who I work for. We have BayesiaLab, that's our product, that's the technology you will see in practice. And then finally, we have Bayesian networks, the mathematical formalism, the mathematical paradigm that Judea Pearl invented. And about all you will hear today. But let me tell you a little bit about our organization. It was founded by two professors in the field of artificial intelligence, Dr. Lionel Jouff, Dr. Paul Monteanu. That was back in 2001, and they had originally developed this technology for their own purposes, but it very quickly became apparent that many other researchers were interested in this technology. So they started a company, and over the course of the last 18 years, BayesiaLab has evolved into a fairly comprehensive software platform, including desktop software packages, web applications, APIs, and of course our book. Our book remains available for download. It's by now about 2 years old, so some of the screenshots are no longer up to date. So we're frantically working on the next edition. So hopefully we can get that to you in the fall. The current edition you can download for free. The future edition will also be available for free download. But BayesiaLab, that's really the core of what you will see today. It's a desktop software that allows you to encode, learn, edit, perform inference, analyze, simulate, optimize. And all of the above you may have seen already some way or another, but perhaps the GIS mapping capabilities, that is probably new to you, and hopefully you'll find today's presentation interesting in this regard. Just one more thing before I get started properly. All the slides, all the data, the networks that you see, all of those will be available for download, including the recording of this webinar itself. So, our motivation today. Now, when we talk about data science and data mining, big data, machine learning, sometimes we get carried away and think about those things in purely abstract terms. But of course, a lot of our reasoning inevitably links back to the real world, or in fact, we may reason directly about the real world. And for many problems, this means we need to look at geography. In fact, spatial reasoning really is now deeply ingrained into our daily lives, and honestly, I couldn't even imagine approaching this intersection without GPS navigation. I took this picture a few years ago in Washington, D.C. So really, GIS, GPS, one way or another, really touches us day in, day out. So how does this relate to BayesiaLab? Well, since version 7, which we released last year in September in Paris, BayesiaLab can do maps. Now, I should say we're not trying to compete with existing GIS technology. Rather, what I'm trying to show you is how we can explore familiar problems in entirely new ways with Bayesian networks. I think it will be interesting to see today that the maps that we produce are all ultimately only for our understanding. What we will do is representing geography through Bayesian networks. And but you will see how that works in practice. Let's talk first a little bit about the basic functionality. And I should say that it's not all BayesiaLab. In fact, Google is doing some of the heavy lifting here. As you may know, Google offers a wide range of APIs, including the ubiquitous mapping API. That is what we're using with BayesiaLab. And the way how we set this up is as follows. Where is the next slide? Here we go. In BayesiaLab, under Preferences, you can enter an API key, and you can either use our pre-configured API key, that's by default part of BayesiaLab, or you can also get your own Google API key. Excuse me. So if you produce lots of maps and you have your own key, then you won't run into any limitations of our shared API key. So that's how you set it up. But let me talk a little bit more about the basics. The way mapping in BayesiaLab works, that you can essentially display any observed or inferred values that have coordinates. Those you can present on a Google map. And we use longitude and latitude as the coordinates. Now, as you bring in data into BayesiaLab, bear in mind that you will still need to discretize longitude and latitude as variables, as you do with any other continuous variable. Even though for display purposes, for map display purposes, BayesiaLab will use these values on an undiscretized basis. So don't get worried if you see that perhaps that too few bins might produce too coarse of a map picture. That will not happen. So how do you go about the mapping function in BayesiaLab? Well, we have a new menu item that you can find in validation mode under Tools, named GIS Mapping. That brings up a window that gives you a number of options. It allows you to specify what variables represent longitude and latitude, and then you can represent 4 attributes of your observation as shape, size, color, and opacity of the item to be displayed on the map. So it gives you a lot of flexibility, and I've been experimenting with this over the last few weeks. It's really interesting what visuals you can create that way. Also, bear in mind, you can use continuous as well as discrete variables. For instance, you can display different types of categorical variables with different shapes, different symbols, like a circle versus a square versus a triangle. But I think you'll see a little bit of that momentarily as I demonstrate that. So let me leave PowerPoint. Okay, now you should be able to see BayesiaLab. And now I want to take a very simple data set, a public data set that represents the average commute time of counties throughout the country. So I'm now going to load a data set that just has longitudes and latitudes of American counties along with the average commute time. So very simple data set. Let me open that. and we would find it here. Oops. Commute by county, that's the file we're looking for. Here we get our preview. In this case, we have two categorical variables up front here, name of the county and the state. Then we have latitude, longitude, and finally travel time. That's the one we're really interested in. In fact, the names and the state we don't even know as we display these coordinates on the map. So let me just click next, next, next. And here I will just leave everything at the default level and just bring in these data sets. Now we have 3 nodes, latitude, longitude, and travel time to work. And without even having to learn a network or anything else, I can go straight ahead, switch into validation mode, go to Tools, GIS Mapping, fill in my variable names. Here they were aptly named longitude and latitude, so BayesiaLab recognizes that these terms match. You can select the shape, the size of the symbol on the map, and here I want to display the travel time to work as a color scale, and finally I will set the opacity to 1. So we have solid objects, solid symbols on the map. Okay, let me run this. BayesiaLab now sends these data points up, and I made a mistake. BayesiaLab sends these data points to Google Maps, which then produces the map. Now, I made the mistake. I highlighted or I used latitude for color scale, which obviously makes little sense. Now I fixed that. Now we have travel time to work here. And now let's run that again. And here we go. Here we now have a map of the US, color-coded as per the travel time to work. And not surprisingly, we have the big cities that pop out in the deep red, whereas out in the countryside, in the Midwest, obviously there we see the green. That's all not at all surprising. And we probably have many tools at our disposal to do something like that. So just wanted to introduce this basic functionality so we can now proceed to something perhaps more interesting. Let me switch back to PowerPoint. Okay, let's now look at some real problems or some interesting problems. And when we talk about optimization problems or spatial optimizations, there are different classes of problems. So here is a bit of an overview, and let's start with the simplest one. Problem number 1, one origin, one destination. That's the traditional navigation task, which is typically about what's the shortest way to get from point A to point B, or perhaps the fastest. So that's the simple one. That's what we do pretty much every day. The second type of question is about how far I could go in a given amount of time or with a certain amount of fuel. So this would be about creating bands of drive time around a possible origin. Basically, one origin, many destinations. We will do that and show how we can do that with Bayesian networks. Next one is many origins, one destinations, prototypical for finding a venue for a new or location for a new venue, store, restaurant, what have you, where it's all about having this new location being as accessible as possible to the widest range of people so they can get to it. Next one is about having many origins, one hub, and then many destinations. This is a prototypical example perhaps for a company that has multiple manufacturing plants and then perhaps numerous wholesalers it ships products to. And perhaps this organization wants to figure out, well, what's the best way to coordinate many manufacturing sites and many customers. Where should the hub go? We will do that too. We will solve that. And then finally, this is what airlines and shipping companies like FedEx and UPS probably do day in, day out. They're dealing with the multi-hub location problem. That goes beyond the scope of today's presentation. But one thing I should state is that with all these problems, there's really a common objective, and that is that we wish to minimize a cost function. And sometimes this cost function could be travel time, could be distance, fuel consumption, number of terms. Somewhere I read that when UPS or FedEx, when they plan their daily routes, they try to minimize the number of left turns. So things like that. And furthermore, we assume that all participants in this system have the same objective. So that we're looking for the shortest path, and then the person who wants to travel is actually his or her objective is to go on that shortest path as opposed to taking the scenic route. So that we're all on the same page here. Now, most often computing the cost is about, well, figuring out what's the fastest. And the basic search is really about looking at the map, finding what is the most direct route. One origin and one destination. And when you do this on Google Maps, they typically give you 2 or 3 alternative routes. But of course, in the background, they may have searched thousands of possibilities. Because of that search, this can sometimes be slow. Well, it's not slow when you do it for an individual route, but if you have to do this for multiple routes or for multiple destinations, as you need to do as you compute drive time rings or drive time bands, then you need to evaluate many possible paths to many possible destinations. For instance, just a few months ago, I was looking at possible colleges for my daughter, who will soon be a senior in high school. So we were thinking about perhaps having her at a college that's within a 4-hour drive time radius. And so I used a GIS mapping tool to compute these 4-hour drive time rings. And that's the result you see on the left. Took about 30 seconds to compute. And then I thought I expand beyond that. But as it turned out, that tool couldn't even go beyond 4 hours. So I was looking for other tools, finally found one that could do an 8-hour drive time ring, but that took a lot longer. So here's the issue, that as you have to explicitly compute all these possible routes, that takes time. So you may say, hey, why don't we take a shortcut here and make things simpler for us? And instead of searching the map directly, which is accurate but relatively slow, why don't we just compute the distance as the crow flies? And in fact, there are very simple formulas that allow us to compute that. But sometimes that may be an unrealistic assumption, or sometimes you may be more interested in travel time than in distance. So here's our idea of how to do things differently with Bayesian networks. Or, well, not quite yet. I'm jumping ahead. First is the interim idea, perhaps. Well, why don't we simply compute all distances between all points in the US? So let's just compute that for once, store it in a big table, and then just look it up. That would be very simple. Well, we could certainly do that. Let's say we do this for all zip codes in the US, roughly 30,000. And but the problem is that matrix, even if we just did it for the zip codes, would be quite large, would be almost like 1 billion cells in size. And that would take a while to compute. Even, actually, I tried it out. I used the Google Distance Matrix API, and that processes about 2 requests per second. With that, it would take us about 14 years to put all that together. I'm sure there are ways to do it faster, but it gives us a sense of how computationally demanding that is. So what is our idea? Well, we're going to approximate. So instead of computing everything explicitly, we are going to figure out how we can capture all these relationships in a more compact way. So what we want to do is we want to approximate through machine learning and use actual point-to-point travel data as opposed to using theoretical zip code combinations. And we can imagine many companies, fleets of trucks, shipping companies, they all have lots of data in this regard because they track where their vehicles go, etc. And with that, we would have very, very accurate and precise data on the movements, where they go, and so on. Now, unfortunately, those kinds of data sets are rarely public. So what we're going to do is we're going to simulate such a data set. And the Google Distance Matrix API that I just mentioned, that's what we're going to use, or what I have used, to generate a synthetic origin destination data set. Basically taking 100,000 random zip code pairs and computing these distances, pretending, well, perhaps those are all the routes of a transportation company. With that, once we take this data set, we will perform naive learning. We will evaluate the performance to see whether that is a good approximation. And then we want to test that out with a new data set with the objective of creating drive time bands that we want to present in a map. So let me switch back into BayesiaLab. Okay, here is what we had before. We can close that now. Okay, and now I'm opening this data set with the zip code pairs that I have mentioned. So this is in this file. So here is my data set, structured as follows. We have longitude and latitude of the origin city, here city, state, zip code, and then here is longitude, latitude of the destination, along with city name and state and zip code. And then finally, we have columns for drive time as computed explicitly by Google. And then finally, also distance that was computed by Google. But we're not going to use all of these variables. In fact, city, state, and zip code we don't need. We'll just work with the coordinates. And then also we don't need the distance. We just want to look at drive time. So let me bring this in. I will use a discretization with quite a few bins because we want to have a relatively fine grid across the US, because we want to make forecasts on the points on that grid. So I'll start off with an R-squared genetic optimization discretization with 25 bins. So let me do that. BayesiaLab now brings in all my variables. But for the target node, what will be our target node, that is time, I want to change my discretization. But first, let me arrange these nodes in a slightly nice way. Let me make those a little bit larger so you can see them on the screen. Let me put time in the middle. And in terms of time, I think we want to look at nice round numbers for increments, so it's easier to interpret. So I'll open this. I'll open the node editor, and instead of leaving it at the original discretization, I will generate intervals and say I want to generate 8 intervals. 8 times 4 equals 32. from 0 to 32, I want to have this sliced into 4-hour increments. So let me do that. Now we have this new discretization table, and I accept that. And with that, I will quickly need to estimate the parameters again. So we now have the probabilities for each time slice again. We can quickly verify what that looks like by opening up the monitor panel. And here we can see the distributions of longitude, latitude, and finally here the drive time. Okay, so what are we going to do? I will declare time formally as my target node and then learn a network. Here I will use an augmented naive Bayes network. Shouldn't take very long to learn at all, and we are already done. So now we have characterized time as a function of origin and destination, longitude and latitude. Perhaps we should check whether this is an appropriate characterization. So I'm running a target performance analysis, and this gives us a sense of, how good is this approximation. So here we have an R-squared of 0.92. Perhaps this is reasonable for our purposes. Later on, we could certainly spend time to further optimize this model. But now we can take this model and infer any point with any real or hypothetical coordinates. And this is exactly what we want to do now, because I now want to play against this model a new data set that just has, for the origin, the very same coordinates, namely the longitude and latitude of our office here in Franklin, Tennessee. And for all the other ones, we have a random selection of zip codes throughout the country. So basically, we want to compute every zip code relative to our current location. And that gives us then, or should give us, these bands of drive times. Okay, let's do that. I'm going back into the modeling mode, and now I'm going to associate a data source. So previously we imported a fresh data source. Now I'm going to associate a new data set with the existing model. I'm bringing this in. This is now a selection of 10,000 coordinates. On the left, we have the target coordinates, kind of all my hypothetical destinations. And then on the right, you see two columns that all feature exactly the same coordinates. That's the coordinates here of Franklin, Tennessee. So let me bring this in. We can just go straight through, nothing to define. BayesiaLab recognizes that the variable names in the data set and in the model are the same, so it automatically associates those names. So with that, finish. And we don't need the report. Okay, what do we have now? What has changed? Well, we see that the longitude and latitude nodes, they are still blue, meaning these are observed nodes, and we have actual data behind it, as opposed to the time node that has turned white, meaning that there is it is not observed. We have no data sets. In fact, that's what we're trying to infer. So there are a number of ways how we could go about this. Since we have associated the data set with this model, I can now simply say or ask BayesiaLab to perform imputation. Now compute the values, the time, given all these hypothetical origins and destinations with this model. Okay, so what do we have? Well, let's evaluate that. We could evaluate this individually, and perhaps let's do that real quick. Let me make up a hypothetical. So I just created a hypothetical pair of origin and destination. And with that, it seems like with what I've selected here, wherever that may be, we would have a drive time of under 4 hours. So we could now manually try out many possible pairs, which would be quite tedious. So instead, we let BayesiaLab map all these 10,000 hypothetical destinations. So go to Tools, Mapping. Now I need to make sure I select the correct one here. So, and I want to show drive time as color. So red means long drive time, green means a short drive time. Now this may take a little bit longer, but not because of BayesiaLab, but rather because we need to transfer this to Google Maps, which then needs to visualize it on a map. And just that data transfer takes a little bit while, not too long here. Now we can see the drive time, or the color is now a function of the drive time. Not surprisingly, the West Coast is all red, and then right around the center of the country, right around Tennessee, where we're located, there is all green, and then as we go outward, it turns yellow. Exactly what we would have expected. But the point here is we have now not explicitly computed the distances, but rather we have simply inferred them from a learned model. So now, of course, we could fine-tune the color scheme, because here I would argue it's pretty tricky to see the transition from green to light green to yellow. But we could certainly improve that by selecting different colors, etc., or using hard thresholds, basically saying show everything within the 4-hour radius in blue and everything else in red, or something like that. So good. That was the example number 1. Fairly straightforward. Let me now return back to PowerPoint. So let's now go to a more interesting problem. And that is, how can we find a single hub if we have many origins and many destinations? Where is the ideal place for such a hub? Now, again, we can't use real data from our customers, so I've made up a fictional data set for a hypothetical company with manufacturing plants west of the Mississippi that are all shown here in blue. And then we have a whole bunch of end users, recipients of shipments in green, and they're mostly east of the Mississippi. So blue origins, green destinations. So, and so far, most shipping was done point to point. And that can sometimes be a problem, because if you have a small load for a small customer, then you cannot fill an entire truck. And so when you then have to share a truck less than truckload, then it becomes less efficient, and so on. So here the objective now is, where should one locate a hub that consolidates all the inbound shipments, and then from where then all the outbound shipments can originate. So how do we go about this? We will encode a theoretical problem. We will encode a theoretical model of our practical problem. For that, we will need to define nodes, observed, unobserved, and I will share function nodes, how they work. We've received a lot of questions about function nodes, so I thought it would be good to show how they work. And then once we have that theoretical model, then we load the actual data of the origins and destinations that we have in mind, that we have defined, and then perform a function optimization. So And I'm sure you've all been waiting for me to bring out this particular slide, our map of analytic modeling and reasoning. No webinar, no presentation of mine would be complete without it. And this slide is about highlighting where this model that we're now building belongs. And here I should emphasize we're going to build a causal model, because we're trying to figure out where to put this new hub, this new distribution hub, this new warehouse. And in that context, we're trying to actively manipulate, we're going to actively manipulate the location of this potential hub. So we will cause this location. We have origin and destination fixed. We're now going to try out different positions. So here's the theoretical model, and this is going to be a very, very busy slide. So I've tried to make it perhaps less daunting by using some animations here. So on the left, the two nodes reflect origins. So, and the coordinates longitude is represented by node lambda 1 and a latitude by the variable phi 1. And I've used lambda and phi simply to follow the convention of the formulas that we're going to subsequently use. So it will just make it easier when you compare the variables here to the variables, or the formulas you find in textbooks. Also important here, we're now looking at longitude and latitude in radians as opposed to in degrees. Again, following convention, it makes the formula a little bit easier to manage. So that's origin. We have the same for destinations, again, coordinates in radians. And in the middle, we have the hub. So again, lambda 2 and phi 2, they reflect the location, the potential location of the hub. And then you see two additional blue nodes that are labeled hub longitude in degrees and hub latitude in degrees. These are strictly for information, so once we get the results in radians, we can actually directly interpret it. I certainly can't picture a location on the map just by reading the radians. So that part, that in the middle, is the hub. That is what we will manipulate. And then we have these two nodes, these two computed nodes, unobserved nodes, distance 1 and distance 2. They will produce the distance between first the origin and the hub, and then they will also compute the distance between the hub and the destination. And as I said, lambda 2 and phi 2, those are the variables that will be manipulated. For those we will try out different values. And then the final piece in this busy slide is the green node, the hexagon-shaped node. Right in the middle where the callout is pointing to, that's the function node, or that is a function node that represents the grand total, meaning the total of distance 1, or the sum of distance 1 plus distance 2. That's what we want to minimize overall. So our objective is to manipulate the hub until we minimize the grand total of the function node. So what do these nodes look like inside? And momentarily I'll switch into BayesiaLab to show that to you in practice. For now, I will share with you screenshots because they are easier to annotate with arrows and highlights, etc. So let's look inside the node for distance. And this is, I probably shouldn't say the familiar formula. There are in fact several formulas how you can compute the distance on a sphere, which we use as the approximation to compute the distance on Earth's surface. Then there are different formulas of different levels of complexity. I'm using the one that popped up first on Wikipedia, and I simply retyped that formula into the node editor. I think most often when you open the node editor, you may just look at the distribution of variables or the conditional probability table that is estimated from data. Here, we're not estimating anything from data. Here we're just saying this node, distance 1, is deterministic. It is computed, or the value is determined as a function of the coordinates of origin and the hub. So then next is, what does the grand total variable look like? Total distance, that is a function node. And the function node does no longer have distributions. There is no table associated. It's rather a single scalar value. And for that reason, we need to perform inference. So we need to take the expected value of node distance 1 and add the expected value here shown in the formula as mean value of distance 2. With that, we have a value, a scalar value for the grand total. So this is now our objective. We have our model, our structural model, our causal model with all the elements. And now we need to manipulate lambda 2 and phi 2 with the objective of minimizing the value of total distance. So let me swap to BayesiaLab again, and if I do this often enough, the switches will perhaps become a little bit faster. And luckily I've already opened this file earlier. So here's the network. This, again, I should emphasize, this was not learned from data. This is strictly based on our theoretical understanding of the world. And here it's really very straightforward. Let me just show you what this looks like. So I have lambda 1 and phi 1. Or I should correct what I just said. This is not entirely a theoretical model. The structure is theoretical. However, the coordinates of origin and destination, they are very much estimated from data. Remember, I said we have these, the green bubbles and the blue bubbles that represent the origins and the destinations. So for that, we have data. In fact, we have a total of 625 pairs of shipping relationships between these green and blue bubbles on the map. And so what you see here in terms of distributions for phi 1, lambda 3, and phi 3, I should probably order these correctly. This is basically the distribution of where these plans are located. All right, so next is we need to figure out where to position our new hub. And for now, we just have a uniform distribution for lambda 1 and lambda 2 and phi 2, the coordinates for our hub. We don't know anything. It could be anywhere. And now we need to figure out how we should change these positions in order to minimize the total distance. So, and I can perhaps also bring up the monitors for the nodes, distance 1 and distance 2. So this is all getting quite busy. Let me perhaps make this smaller and allocate more space to our monitors on the right. Okay, now we have everything in view. Of course, we could now simulate different possible locations. I could just make up values for lambda 2 and phi 2 by clicking, and that as I define values, then I can update the distance values, and as a result, I get an updated total distance. Of course, this would be very tedious to try out every possible combination, even though we only have two variables to manipulate. But you see, with what I just randomly set, my total distance would go down from an average of 2,366 miles to 2,063 miles. But let's now pursue this more systematically and let BayesiaLab search for the optimal values of lambda 2 and phi 2. So I go into function optimization and select genetic. So and this now allows me to search. Sorry, I forgot something. I need to select lambda 2 and phi 2 as the variables that I wish to optimize, because the other ones I cannot optimize. I cannot move my manufacturing plants. I cannot manipulate the distance. That is rather a resulting variable. The only ones that I can manipulate are the coordinates of my potential hub. So now with those selected, I go into function optimization to genetic, and now I have a number of options. My target node indeed is total distance. That's the function I wish to optimize, and I can now set any value I wish. Now in our case, I could aim for a specific target value, but much more plausible would be just the lowest possible value. So ideally, zero distance. We know that's not possible, but directionally, that's where we want to go. Next, we need to determine how we search for these values. Now, here we're looking for a specific point. We're not looking for a distribution. There are other optimization problems where we're looking for a distribution of the variable that we want to optimize. Here, we want a point estimate, and therefore we need to select binary. And I will select 10 intermediate points. I should, if we had no time constraint, I would probably search more points. I leave all the genetic settings at their default. And then the only other thing I set is the stop criterion, because genetic search algorithms keep going forever unless I stop them, or unless I set a criterion that stops them. And here I'm saying, unless you find, or if you can't find any better solution after 5 iterations, just quit and give me the results. So that's what we're going to do here now. And I'm opening up the console here at the bottom. And that gives us a preview of the solutions that are being considered. And the ones that are highlighted with the triple asterisks, they are the best ones so far. And you can already see that this is converging to very, very similar values. It's still trying to look left and right. Could we find something a little bit better? But I think, yeah, here's the result. This is what we found. We started here with the initial state, which wasn't really a state, but rather just the expected value of the uniform distribution. What is of interest here is the best solution. Where should we locate this place? And what is the new total distance for all, the average total distance for all transportation trips? Yeah? And so here, with the solution we have with these values for lambda 2 and phi 2, our new average distance is 1,633 miles. Now, BayesiaLab, based on what I said earlier in the options window, has automatically saved the best value, the best solution. Here in this case, we only have one solution. There is not really a backup solution. I can recall that and bring it up. So here I can now show what the actual values are for lambda 2 and phi 2, and then what the corresponding distances are. The distribution of distance 1 and the distribution of distance 2. And then of course we can look at what is this in degrees. So I'm just bringing up the monitors of the nodes for hub longitude and latitude, and with that we can read our results in degrees, which we can then immediately look at on a map. So switching back to PowerPoint, and here is finally the optimal hub locations. Latitude 40.691, longitude minus 86.687. That happens to be right outside Lafayette, Indiana, roughly in the middle between Chicago and Indianapolis. And so this would optimize our hub location problem. And looking at this seems quite plausible. So now I've taken you through how we can use a Bayesian network. Or before I move on and get to the concluding remarks, you may now say, hey, you know, why didn't we learn this? You know, why did we compute distance 1 and distance 2? Couldn't we have also learned those distances? Absolutely, we could have, like we did in the drive ring example, where we just learned the distances, the drive time from the actually observed data. Well, the reason why I wanted to show this alternative approach is how we can directly use equations in Bayesian networks when we have theoretical knowledge, such as the formula for distances on the surface of a sphere. But of course, we could have used, had we had the appropriate data with the appropriate mileage data and so on, we could have used, instead of a formula for distance 1 and distance 2, we could have used a node that represents the conditional probability table that links the coordinates. So I've just chosen to kind of take you through a spectrum of functionalities, and we've had quite a few questions about how to use formulas, so I thought this may be the appropriate point to introduce those. So in conclusion, we have more webinars and seminars coming up. The next one should be quite interesting, will be about health outcomes research. That will be 2 weeks from today. We also have a physical seminar coming up that's going to be in Chicago. This will be about knowledge discovery in financial data. That will be a 3-hour seminar, basically the entire afternoon. And for all of these events, you can register online. Now, one more thing, what continues this year is our 3-day course program. In fact, today, my colleague, Dr. Lionel Jouffe, is completing or concluding the 3-day introductory course in Seattle. So on social media later today, you'll probably see some photos from our course group. Our next course in the US will be in Boston at the end of June, then at the end of July in San Francisco, and so on. We're in a major city somewhere around the world once a month. And then, of course, I encourage you to get a trial of BayesiaLab so you can experiment with all the data sets and networks that I've shared today. I should mention we have 2 types of trial versions, a simpler one that you can immediately download, and then an unrestricted one for which you need to apply, where we would simply like to know who you are and what you intend to do with it. So That's available to you. And then, of course, I'd like to encourage you to join us on our community, on our website. Great place to exchange tips and tricks and learn about how other people work with Bayesian networks in BayesiaLab. And of course, as you hear from me in every webinar, please join us for our annual conference. This year we will be in Chicago. Should be a great event. We have researchers, scientists, practitioners, business analysts from all over the world come and join us. It's a great venue, of course, a great city. Who doesn't like downtown Chicago? Perhaps architecturally one of the most fascinating cities in the world. And our venue is right next to the John Hancock Tower. So a really cool place. Great group of people, and I hope that you will join us. So with that brings us to the end of today's webinar. On behalf of our team, I'd like to thank you for your time and interest. Please do feel free to reach out to us with questions about Bayesian networks or BayesiaLab. We'd be happy to speak to you one-on-one about your potential use cases for our technology. So with that, thanks again. I hope to see you in 2 weeks at our next webinar. And in the meantime, have a great weekend.